All right, so the Arrhenius concept you're familiar with acids and bases. The acid produces an H plus, the base produces an OH minus. The problem is we have things like ammonia, which when I go stick a piece of paper, a piece of litmus paper in it, it turns blue. So we know for a fact that it is a base. But it doesn't quite fit this definition very well at all, right? So we have to have another definition that's a little more inclusive. Please don't fall out of that chair. So the next definition is the Bronsted-Lowry definition. This is the one we will use pretty much for AP Chem. There is a Lewis acid and base as well, and it keeps track of electrons. That one is no longer tested on the AP test, but I can promise you'll see it in college. So we'll mention it, but you won't be responsible for it. All right, so the Bronsted-Lowry definition, what does it say an acid does? Donates an H plus. What does it say about a base? It says it accepts the H plus. So with the ammonia, if I have an H plus sitting somewhere in solution, I can make NH4 plus. So this is functioning as a base, and if you see it this way, might be. That wasn't what I was going to do. Well, let me just do H plus and just leave it at that. Oh, wrong thing. Okay, so here it's functioning as a base. This is your acid. Here you can see your acid, whatever the H plus is, and then it makes something. All right, most of what you're familiar with acids and bases. NaOH plus HCl. What does it make on the other side? Think regular double displacement. Water and a salt. It's going to make H2O plus NaCl, right? And so this is our base. This is our acid. On the other side, though, we're going to have things that are conjugate acids and conjugate bases from these parts. What parts of these actually reacted, though? So what part makes it acidic and basic? Yeah, if you write the net ionic for that, you really end up here, right? And this is water and a salt. This salt, though, is still soluble, so it doesn't, right? The Na pluses and the Cl minuses are just still running around in the water. This is the part that actually reacts. And really, you're going to end up with this. And if we, because just so I can show it to you. So this OH minus, I don't want to show it to you that way. No, I don't want to show it to you that way. This is what I get for not looking at it. All right. So there's your net ionic. So a strong acid and a strong base make the water and a salt. All right, let me follow your notes so that we're paying attention. Think about just an acid. Pick an acid. HCl, HNO3, anything that doesn't have two H's. Let's just start with things that are monoproduct, that have one H. When it dissociates in water, so if I put HCl in water, it's going to dissociate to have an H plus and a Cl minus. They will either write it like this, or you can write it, actually this one's a strong acid, I probably shouldn't write the equilibrium. You can write it like that. My point being is that these two things are the same thing, okay? If you include the water in your reaction, you must include H3O plus on the other side, because that's how the H plus actually exists in solution. If you drop the water, then you can just put the H plus. Either way is fine. The Ka, that's what we're defining. So new K. New K, right? So we've done Kc, we've done Kp, we've done Ksp. This one's Ka. It's all still equilibrium, though. This is the acid dissociation constant. What does that mean?
It's It's the rate at which the acid is
Yeah, so this acid is dissociating, right? So a Ka would go to a reaction that looks like this. Okay, do you remember your strong acids and weak acids? Oh, they're coming back. Let me see if I put them on your notes. Huh? There are 7 strong acids. You should know them. You should know them. Do I have them listed? No. All right, so let's list them because you're going to need them. All right, so strong acids. Write them down somewhere because I didn't type them in your notes because I've expected you to have them memorized.
Wait, you are recording this, right?
Yes. All right, what are your strong acids? HCl, HNO3, H2SO4. We got 3 of 7. Keep going. HBr, HI. We're close. HF is not one. HClO3 and
Acetic acid.
no. HClO4. Those are your strong acids. Memorize them because anything that's not strong acid is a weak acid. You must memorize them. Okay. We really say there is no Ka for strong acids. Why do we say there's no Ka for strong acids? They don't dissociate? They completely dissociate. So they completely ionize or completely dissociate. So the Ka would be really, really large, like infinitely large, right? So we basically don't have Kas for strong acids. Okay? They completely ionize in water. Okay? Those make life easy. Let's look at a little, look. Remember, if we're looking at something in water, okay? Water, we'll talk about water. It auto-ionizes in the first place. But we'll talk about that in a second. Look at the strong acid. What happens when I put the strong acid in water? Is it big enough to even see? Oh, except for you can't see the thing at the bottom. Are there any of the acid, the original acid, left in solution?
No.
No. So the assumption is that a strong acid, every bit of the acid dissociates or ionizes into the anion and the H+. What's going to happen when I click weak acid over there?
You're going to have some gray stuff left.
I'm going to have some gray stuff left. Right. So the weak acid is going to ionize some, but not very much. Are most of them dissociated or are most of them together? Most of them are actually together. This is when we have a Ka, right? So our Ka value is basically going to tell us how much that acid ionizes when it's put in water. Just like it told you how much something dissolved in the water when we did the KSP, right? The bigger the KSP, the more that it would dissolve. The bigger the Ka, the more it will ionize. What does that mean then to pH? Well, we have to define pH. What does that mean to pH? Whoops, I clicked on something. I don't know what I clicked on. All right, we said it had something to do with the H+ concentration. This thing hates me. Yeah. So pH is defined as the negative log of the H+ concentration. Or if we're going to write it with the H3O+, it's going to look like that. So in strong acids, it's very easy. Chandler, just because I'm recording it doesn't mean you don't do anything in class. Because I'll turn it off and make you take notes.
Ooh.
The pH of a strong acid makes life really, really easy. Because if we have HCl, all of it turns into H+ and Cl-, right? So if I have a 1 molar solution of HCl, how much H+ am I going to have? Yeah, 1 molar and 1 molar, and this is going to go to 0, right? So what would be the pH of a 1 molar HCl solution.
-1.
Which is what?
-1/10. What am I doing?
What's the log of 1? It's 0.
0.
It's 0. Okay. So mathematically, if we really had higher, Luke, if we really had higher and higher concentrations, mathematically you could get things that were outside of our pH scale, which is usually 1 to 14, right? It ends up being a solubility issue if they get too strong. But anyway, so if you get something lower than a 1, you're okay. You probably won't on the AP test. So strong acids are easy. What happens when, well, okay, let's leave it at that. Strong acids are easy. All right, what about water? Water is both an acid and a base. Water will split up into H3O plus and OH minus on its own, right? Go back to our little simulation. What happened when I put water?
It breaks down.
Yeah, so water auto-ionizes into the H plus and the OH minus. So the pH is always 7 because the H plus and the OH minus are always equal. Huh?
That's crazy.
It is. They're equal to each other, so they offset each other. All right, so water auto-ionizes. There's a K for water, too. Aren't you thrilled?
Yes.
Yes.
That's how many K's?
There's so many Ks. That dissociation reaction for water, or the auto-ionization reaction, whoops, not two, for water has its own K. This is KW.
K water.
K water, KW. Okay? All right. It changes with temperature, but with it being room temperature with 25 degrees, KW is 1 times 10 to the -7th. What does the KW's expression look like for water?
H3O.
Yeah, why doesn't the water not go on the bottom?
Because
Yeah, it's that pure liquid, so it didn't go on the bottom. So the KW expression is the H3O plus times the OH minus. And we know that equals 1 times 10 to the -7th. What do we know about H3O plus and OH minus for water? They're always equal, right? So this is 2x equals 1 times 10 to the -7th. What's x? I mean x squared, because I can't do math because it's been a long day already and it's only second block. Yes, thank you. X squared equals 1 times 10 to the -7th. So if we take the square root of both sides, what do you get? Yeah, which is? Should be the 14th, is it not? Should be the...
Squared, wouldn't it?
Mm,
Shouldn't that be squaring?
yeah, but
It's 3.2 times 10 to the -4.
if we take the square root of that,
You squared 1 times 10 to the -7.
yeah, I did square it. I was trying to go somewhere with that and messed up.
Here it is.
Why am I bringing the 14th? What? No,
What's happening?
I lied. I've got them backwards. That's what I did. I was like, I've done something wrong. What'd I do? I've got them backwards. Told you it wouldn't be a good video. Dun, dun, dun. This is -14. This is where I messed up. This is -14. This is -14. I'm like, I did something wrong. I'm like, this is not right. This is -7. There we go. Now it's right. Right? Because 1 times 10 to the -14th, and if you're doing the square root, you divide it by 2. I just did them backwards. Brain dead today.
Wait, so KW doesn't equal 1 e to the -7?
Oh my goodness.
What's the matter?
That's
I just
crazy.
mixed up the numbers. All right, so KW is 1 times 10 to the -14. So the H plus and the OH minus are going to be 1 times 10 to the -7th. because they have to be equal to each other. This is at 25 degrees. If you're not at 25 degrees C, this number changes. So if it changes, it's very rarely going to change for you, but it could. All right, huh?
So that's the,
They'll tell you what it is. They'll give you what KW is. So like if they change it to 50 degrees, they'll tell you KW is this number, and then you use that number. So it's no big deal. If otherwise, you have to just make the assumption that it's at 25 degrees and use 1 times 10 to the negative 14.
so when it's a liquid, is it still called solubility for X?
When it's a liquid, is it still called? So you're talking about this reaction?
For X, what would X be called? Solubility.
Why are we still eating?
Not.
No. We've already had snack time. All right, you look at the sample exercise in the middle of page 3. Y'all have calculate H plus and OH minus for the following solutions, and then state whether, state whether the solution is acidic, basic, or neutral. And page 3. All right. They're giving us that the OH minus concentration is 1 times 10 to the minus 5th. What do we know about KW? Now that we got it correct, what do we know about KW?
It's always like that for us.
It's 1 times 10 to the negative 14th. And if this is a solution, what do we always know that H plus times OH minus is going to equal KW? So if we know the OH minus is 1 times 10 to the negative 5th, and we know this is 1 times 10 to the negative 14th, yes, what is X?
Times 10 to the negative 9.
To the negative 9th. What's the pH? What's the formula for pH?
Negative log.
Of the H plus. So if I take the negative log of 1 times 10 to the negative 9, 1 times 10 to the negative 9, what do I get?
Sure.
9. Okay, you got to be good enough at logarithms to do this without a calculator.
Wait, what?
On the multiple choice part of the AP test,
Because that's just times.
Yeah.
What is that?
It's just take the power,
Can you
the
re-explain
negative
log?
power.
yeah, that's what we're getting ready to do. All right, so right there is how I knew the pH. So take your calculators out. Everybody get your calculator out.
Wait, why would that?
I get it.
Because I said so. Get your calculator out.
You just take the these people are evil. Okay.
Take the negative log of 1 times 10 to the negative 7th.
Peter said log. Oh, so that's actual log.
7.
-7.
What's the negative log of 1 times 10 to the negative 8?
8.
8.
Yeah, that's not complicated.
Okay, so now do 2 times 10 to the negative 7. Do the negative log of 2 times 10 to the negative 7.
What's a 2 what? 6.69.
Whoops, 6, 9. Do 2 times 10 to the negative 8. 7.7, right? All right, do 9 times 10 to the negative 7th. So do the negative log of 9 times 10 to the negative 7th.
6.
Okay, 6.05, 6.04. Now do the negative log of 9 times 10 to the negative 8. Okay, we're starting to see a pattern.
Magnitude.
Just magnitudes, right. You're not going to have to pick anything off of a multiple choice down to between 6.04 and 6.2, okay? But you should know that if it's the negative log of 1 times 10 to the negative something, that the pH is going to be that something. When you have something other than a 1 there, what does that do to the answer? It lowers it. So the bigger this number is right here, the closer it is to the next down, right? The next number down. So if this goes to about a 5, about where would you expect, let's make this 10 to the negative 4th. What would you expect that pH to be?
3.4.
Somewhere in the 3.45 range, right? Somewhere less than 4, about in the middle of less than 4, not quite to 3, right? You should be able to do that without a calculator. They're not going to give you 3.4 and 3.5 and 3 point, right? They're going to give you 3.4, they're going to give you 3, they're going to give you 4, they're going to give you a big enough range that you can figure it out. Okay. All right, so you do the next one. Do B and C. Do B and C. Find the H plus concentration and then find the pH.
How does that work?
Huh?
How does that work if you have 10 molar H+?
It's
Then it's like pH of 15.
Huh? 15?
Yeah, because it's part C.
It's not 15. It's the negative log of 10.
I thought you had this.
No, but you do have to find the OH.
Oh. Just, okay.
It was gonna be less than C. When it was negative 1 times 10 to the negative 15.
Ah.
But when you look at 5 times 10 to the negative 1, it's gonna be less than
This thing only likes one mouse at a time.
I don't get it.
3.
What's the matter?
Yeah, pH.
You can mathematically.
Okay, fair enough.
Mhm.
How much do we drink that?
Does that mean it's a really
Probably not
strong,
good for you.
does that mean it's a really strong acid?
Be careful thinking concentration versus strong. Strong does not necessarily mean its pH is low. I can take a strong acid and get a pH higher than, get it closer to 6 or 7 or 5 if I have a really, really, really low concentration. So don't mix up strong and weak equal to pH. Typically, strong acids are going to have a lower pH than weak acids, right? If I have the same concentration. So if I have 0.1 of a strong acid and 0.1 of a weak acid, yes, the pH of the strong acid is going to be lower than the weak acid. But if I had a really, 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 really low concentration, it's not going to be as high. So do not mix up strong acid, strong base exactly with pH. What was your question?
I didn't say anything.
Oh, all right. So Kw is OH minus times H plus. Kw is 1 times 10 to the negative 14th. This one's 1 times 10 to the negative 7th. Oops. So what does the H plus have to be? Same thing. 1 times 10 to the negative 7th. So the pH is the negative log of the 1 times 10 to the negative 7th. Whoops. Which is 7. All right. What about the last one? That's the one you don't like. 10 molar H plus. So the pH is easy because it's the negative log of the 10. What do you get? Negative what?
1.
Negative 1. What's the OH minus concentration?
1 times 10 to the
Negative 15th. Because we still have to find it this way. And when we divide by 10, then the OH minus is 1 times 10 to the negative 15th. Okay? All of this KW stuff leads us to really nice, some nice correlations. All right, let's look at something called, well, do we want to look at, I guess let's look at that. Huh?
Is that acidic or basic?
Oh, acidic. Acidic. This one's neutral, and the first one was basic, right? This one's basic. What?
It just has to be below 7 to be acidic.
Yeah.
Yeah.
Okay, so look at the next example. It says at 60 degrees, Kw is 1 times 10 to the negative 13. Yeah, what does that have to do with anything? Look, what's going to happen? Using Le Chatelier's principle, predict whether the reaction and it's our water ionization, oh, H3O plus OH minus, is exothermic or endothermic. So Kw at a higher temperature, they get bigger or smaller?
Bigger,
The original one at 25 degrees is what?
bigger, 10 to the negative 14.
So it got bigger. So it got bigger. So what did you get more of? Products or reactants? You got more products. So we heated the temperature up, and according to this, we got more products, right? Yes? So is it endothermic or exothermic?
Endothermic.
Endothermic. Heat has to be on this side. If I increased heat, it shifted that way to make more products. So K got bigger. Okay, that's logic you should be able to use. We also should just be able to use this number. What if they gave us, I don't, does the next one, okay, so the next one says calculate the H plus and OH minus in a neutral solution.
You got the one where you have to be equal.
Yeah, they have to be equal. They have to be equal. So in this case, what are we going to end up with? 6.5, which is going to then come out to be what?
3.2 times 10
To the negative 7th? Okay. All right. So again, your concentrations are going to change if your KW changes. But it works the same way. Not going to happen often. All right, flip to page 4. Some nice equations that you're going to use over and over and over and over and over again. It's not horrible. It's not horrible. And then when we get to weak acids, it's just ice tables again. It's really not bad. All right, so pH scale. We know this one. So what do you think POH is? The same thing, right? Okay, that's really all I ever use. The nice thing is the pH plus the POH has to equal 14. This is true at 25 degrees, right? Because the KW part. All right, how do we solve if we have to solve for H plus? Like, what if H plus is the X? How do I solve it?
Multiply by negative 1, raise to the 10.
Multiply by what?
Negative 1,
And do what?
raise it to the 10.
Raise it to the 10. So it's 10 to the negative pH. Yes?
Yes.
Yes.
Okay. So make sure you can do that and get both back and forth.
Wait, what did you just do there?
Anti-volt.
Oops, POH. Yeah, it's your, right? Think about your logarithms, right? Here's math class. You divide by negative 1, so you get negative pH equals the log of H plus. To solve for H plus, you have to raise both sides, right? And then this is the way I was taught. And then that cancels out. So 10 to the pH equals
This is 5.
H plus.
Like, do that on your phone? Like,
Huh?
Why don't you do that? Why?
Why did I do it? Because you're going to need it later. I'm just asking, you know, what if the problem asked you for H plus instead of OH minus, or instead of pH? All right, let's look at the next sample problem. How can we attack this one? It says, suppose the hydronium ion. What's the hydronium ion?
H3O.
Right, this is the H3O plus. Concentration of vinegar is 1.6 times 10 to the negative 3. What's the pH? Easy, right? How do we find it?
Negative log of H plus.
So stick it in your calculator. Somebody tell us what it is.
2.8.
Okay, look at the next one. The pH of seawater is 8.3. Calculate the POH, the H plus, and the OH minus. How are we going to do that? Okay, POH we can subtract from 14. So the POH is 14 minus the 8.3. What does that give us?
5.7.
5.7. How are we going to find the H plus?
Use the other formula. To the negative
Mm-hmm.
8.3.
10 to the negative 8.3. So what is that? What?
Is 5 times 10 to the negative 9.
Oh, I wrote that wrong. 5 times 10 to the negative 9. Is that right?
Yes.
Okay.
The negative 8.3.
Because that's 8.
Because pH equals the negative log of the H plus. We know 8.3 equals the negative log of the H plus. I move the negative over. To solve for H plus, you have to raise everything because these are log base 10. Just like if they were natural logs, it would be e to the whatever, right? These are log base 10s. So that's where that came from. And then now the OH minus, you can find one of two ways. You can do OH minus times H plus equals 1 times 10 to the negative 14th. Or you can do OH minus equals 10 to the negative POH. I tend to do it this way. But you can do it either way. Either way is fine. So tell me what the OH minus concentration is.
2 times 10 to the negative 6.
Somebody else get that? Okay. All right, we should be able now to do the 2 sample problems after 16.5. So we're going to skip those. Let's go to strong base. What are the strong bases? We don't have a periodic table in here, sorry. What are the strong bases?
Anyways,
Yeah, it's the group 1, right? Hydroxides. And then there are 2 more, and sometimes the calcium and the barium from group 2 are somewhat soluble and they're strong. Occasionally you'll see magnesium. It's just not very soluble is the problem. Okay. All right, so let's look at this problem. Calculate the pOH. Oh, no. What is the pH? So they want to know the pH of a 0.011 molar CaOH. Oh, goodness. I can't write. CaOH2, calcium hydroxide. All right, well, we can't stick it straight into pH equals. What are we going to do?
find the molarity of the hydroxide.
All right, find the molarity of the hydroxide. What's the molarity of the hydroxide? You got to multiply it by 2. Why do we have to multiply it by 2? Because there's 2 of them, right? For every calcium hydroxide, you have 2 moles of OH minus. So oh, look, I didn't write it all in. Jeez. 0.022 molar OH minus. How does that get us to pH? Okay, you can do pOH as being the negative log of 0.022. Tell me what that number is. Okay, is that the pH though?
No, it's a PO.
Right, so we have to do pH is 14 minus that. So what do we get?
12.34.
It's all right. All right, how else could we have done that? What if we didn't stick it into pOH? What if we were here and all we knew was this? What else could we do? What's another way to do it?
They have to multiply to.
Right, you could do that the OH minus times the H plus equal the 1 times 10 to the negative 14th. And you could find the H plus concentration this way. And then from there find the pH. Do you like that way better? Don't care? Don't have a preference. All right. We need to practice some before we do weak acids. All right, let me stop this.